Hi, statistics. We're going to continue talking about transforming data. When we are together, we are looking at a set of scores. And we talked about that if I added a couple points to each test, what would it do to the shape, center, spread of the distribution? And we noticed that this shape was going to be the same. It was all going to be scooted up, which means that the mean, the center, is going to change, but the spread would be the same, right? Everything gets scooted up, so the max and min don't actually impact the range because the distance between the values will be the same. We also saw that if we take that distribution and multiply it by a number, the shape will not change again. However, it does get more spread out and the mean will change. So what does this mean for a problem? Well, let's try. In 2010, taxicabs in New York City charged an initial fee of $2.50 plus $2 per mile. As an equation, that means the fare of the ride is equal to 2.5 plus 2 times the number of miles driven. At the end of the month, a businessman collects all of his taxicab receipts and calculates some numerical summaries. The mean fare he was paid, so the average fare was $15.45, and the standard deviation of fares was $10.20. What are the mean and standard deviation of the lengths of his cab rides in miles? So we want to change these from the fare paid to the number of miles. We want to find x bar m and s of m. How are we going to do this? Well, of course, we have an equation that transforms one into the other, but we have to remember what we know about mean and standard deviation and how they change. Mean did change with addition, subtraction, multiplication, and division. All of those are going to impact the mean. We noticed, however, for the standard deviation, the things that changed it were multiplication and division. Standard deviation is not impacted by addition and subtraction. So what does that come into for this problem? When we're figuring out the new fare, or excuse me, the new miles driven, for the mean, we're going to use both of the numbers in this equation. We're going to do both the addition and the multiplication. So the average fare was $15.45 is equal to 2.5 plus 2 times x bar m. We're simply going to solve this equation because mean is impacted by addition, subtraction, multiplication, and division. Solve this like you normally would, right? We subtract 2.5 and then divide by 2 so that we get the mean number of miles driven as 6.475. I realize I just kind of went through that quickly, but I'm just going to say again, we subtract 2.5 from each side and then divide each side by 2. Divide by 2. With the standard deviation, however, standard deviation is not impacted by the addition and subtraction. So when we put our 10, oops, I want that to be darker, 10.20 is equal to 2.5 plus 2 times s of m. When we're trying to solve this, if I subtract this 2.5, it doesn't actually impact the standard deviation. So we don't need to worry about that part of the equation. The only thing we need to worry about is dividing everything by 2, which means that the standard deviation of miles driven is 5.1 miles. The big takeaway here, if we are transforming a set of data, we know that the mean gets impacted by addition, subtraction, multiplication, and division, whereas the standard deviation is only impacted by multiplication and division. One other topic to cover in this section is something called a density curve. So let's remind ourselves of what we do when we are exploring quantitative data. Of course, quantitative data means data with numbers. So the first thing we want to be reminded of is that we always need to plot our data, make a graph. If we're talking about quantitative data, this graph would be a dot plot, a stem and leaf plot, a histogram or a stem and leaf, dot plot. There was one, oh, box and whisker. Once you have plotted your data, the next thing we want to do is look for overall patterns and departures from that pattern. We know this. Our SOCs, right? Look at the distribution and describe it. We are then going to calculate a numerical summary to briefly describe the center and spread. And that would fall into the SOCs describing our distribution. We would calculate the mean or calculate the standard deviation. But the last thing here is sometimes our overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. This smooth curve is called a density curve. What would this look like? Well, let's say I have a histogram. I'm going to draw kind of a histogram right here. I'm going to make it skewed to the right. Well, this histogram here, and any histogram really, can be made into something called a density curve. It's very simple. A density curve is simply a rough outline of the curve. Oh, I did not want to do that. Sorry, I was not trying to change the color. I want to draw a rough outline of this curve. So notice how when I drew that, some of these bars are going above and some are below, and that's okay because we're looking for this pattern that this distribution describes. This is now a density curve. It's a faster way to draw what we had been drawing. In fact, we could pretend that this density curve we just drew is the ages at DSHA. We have talked about this a few times, right? That the youngest students are freshmen, probably 14, maybe there's a couple who are 13. And then we get all the way up to 14, 15, 16, 17, and 18, right? So the majority of our students are 13 to 18. And then, of course, we have some faculty members who are in this general range from 18 to maybe, let's say, all the way over here, 65 would be retirement age. Now, I'm not saying that there's a teacher that is 65 here. I don't know. But this distribution shows the ages at DSHA. There's a couple of important things about density curves. The first is that the area under them, the area under the curve, is 1. Another way to say that is that your density curve represents 100% of your data. So over here again, ages at DSHA. This distribution is showing all of the students and teachers in this building. 100% of our faculty and staff and students lie in here. If I tell you, let's say I know that between the ages of 40 and 50, maybe, this little bit of area, this shaded part right here, let's say I know that 10% of DSHA is between the ages of 40 and 50. I don't know. That's a fake statistic I just made up. But let's pretend it's true. If that is, that means this shaded area right here is 10%, which would mean everything else over here and over here must add up to 100, would be 90%. We can extend this to remind ourselves about mean and median and where they lie in a distribution. So I've got two density curves. I'll make this one skewed to the left. This one is skewed. This is symmetric. Where would the mean and the median lie? Well, mean and median of a symmetric distribution are going to be pretty much smack dab in the middle. In a skewed distribution, median is by most of the data, and the mean gets pulled out into the tail. The other thing that we could note is the median is where exactly 50% of the data is. So 50% to the right, 50% to the left. Notice how in a symmetric distribution, it's pretty easy to tell that those are equal. In our skewed distribution, this area right here looks a little different than this area right here. But if it truly is the median, then those shapes will have the same area. Good luck on your homework. Let me know if you have questions, and have a great rest of your day.